All right. Hello, everyone. My name is Michael. I'm the CTO of NewCipher, and I wanted to talk about how to share data while it's encrypted in a scalable manner. So this talk is more like, well, there is already some system which allows to share encrypted data being developed in Swarm. So I wanted to kind of to start a conversation with the Swarm team about what ways are kind of more optimal or like more scalable for different situations when you share data while it's encrypted. And mainly, I will compare two ways to share encrypted data. One is the approach we are using in NewCipher, which is using proxy re-encryption, and another is correct me if I'm wrong. I think Danny probably can do that. Another approach is using kind of trees of keys, which allow to share data between multiple users pretty efficiently. So I will first overview different methods, their scalability properties, and when I think one method has advantage over the other, and vice versa. Okay. Well, first of all, just for those who don't know what proxy re-encryption is, it's a cryptographic primitive which we use in NewCipher. This is some cryptographic primitive which allows to transform data which was encrypted for one person to be encrypted for the other person. So, for example, over here, data was encrypted for Alice, although Alice, Alice is here. Alice can read this data. This data could be encrypted by someone else, and Alice can grant permission to Bob and Charlie by creating so-called re-encryption keys from Alice to Bob and from Alice to Charlie, and using those, some untrusted proxy can transform ciphertext which was created for Alice into being encrypted for Bob or for Charlie. So proxy, or we call proxy Ursula, another character, can convert re-encrypted texts for whoever Alice allows to convert. So proxy can be used for access control. Well, if you have just one proxy, it doesn't sound very much decentralized. So, and what we are doing is we're actually splitting the operation of proxy re-encryption into multiple proxies. So you require m out of n proxies to actually be converting ciphertexts to get them converted for Bob. And if some proxies are malicious, if there are only a few of them, that's still fine. Right. Okay. No, they actually malicious proxies cannot ever decrypt the data. Even if they come together and do their malicious things like collusion, they would probably only be able to transform this data for Bob, to whom Alice granted access in the first place, but they wouldn't be able to reconstruct the ciphertext. You probably would ask why wouldn't Alice just give some key to Bob to be able to permanently decrypt? But the thing is that here proxies can apply any conditions. Like, for example, I want to allow Bob to read this data only when this happened, or only until that time, or maybe I can revoke the access, and then Bob cannot read the data. So malicious proxies would be able to say, okay, I'm not going to follow these requests anymore. I keep the re-encryption keys and continue re-encrypting for Bob. And if all the proxies do that, then it's too bad. But they couldn't be able to read the data, to decrypt the data themselves. So that's kind of how it works with proxy re-encryption, and with NewCipher, which is the network of these proxies incentivized to work properly. Right. So, well, let's just look at different ways to share encrypted data from scalability point of view. So for that, let's just say M is number of messages you've sent and received, P is number of participants in multi-user setting, and let's say G is number of grant revoke operations, right? And let's say we're probably using some public key cryptography, which is relatively heavy weighted. So yeah, and we're interested in number of these heavy weighted operations which we do. Well, what's the naive way to share in, let's say, just for simplicity, imagine a multi-user chat. Everybody sends message to some group, and everybody else in the group has to read messages in the chat. The most simple, like dumb way to create this would be to encrypt for everyone. So I have P participants, and then you pretty much encrypt, like every user who sends messages would encrypt messages for everyone in this group chat, and do O of P or like number of operations. So it's like to encrypt, to send message, you need to do number of operations proportional to number of participants, and also number of communications proportional to number of participants. So it's kind of, well, not convenient, or if you store those messages, not storage efficient, and also like the participants would need to be able to store, like to have at hand all public keys for all the participants. Well, is it possible to do better? Well, obviously you can use proxy re-encryption, but I'm not talking about that. Let's say we do sessions, like when a new user joins, a new user leaves, you have a new session starting. And let's say you have session keys. The dumb way to do it with session keys would be that you have an admin in the group who like sets a new session key when the grant or revoke happens, and sends this session key to every participant in the group. Well, then this admin, with every grant, this admin should do O of P operations, like number of operations proportional to number of participants. And, this admin of the group should be online all the time, and or at least all the time the grants and revokes happen. And then, this admin should exist, which is probably not super cool. Not always super cool. And other than that, after this operation happened, everybody can use session key to read messages in the current session. So is it possible to do it better? Well, and I think I believe that's something similar to what Swarm uses currently, is using kind of trees of keys, which allow you to do to do it so that after every grant revoke operation, every participant in the group has to do O of log P operations, like where P is like number of participants. So you have to do a kind of logarithmic work. And also this, this is probably coming from this paper, on end-to-end encryption, called asynchronous ratcheting trees. So in this case, no central admin is needed, and this achieves perfect forward secrecy, which actually comes with pluses and minuses. The biggest plus of the perfect search for secrecy is its privacy properties, and it's also its big minus, because by definition, perfect forward secrecy is that the new user cannot compromise the sessions which he wasn't involved in, so he cannot read the past, he cannot read the future if, let's say, somebody revoked this user. So, and not being able to read the past means no access to the history, unless somebody explicitly sends this user all the past session keys. So how would this ratcheting trees work? just to kind of give a brief overview of my understanding. And again, I think that's maybe what Swarm is using right now with access control, but correct me if I'm wrong. I don't know who is the best person to answer that. But anyway, so how those trees work is that, like, imagine that every user has his key pair, like private and public key. Let's say lambda 1, 2, 3, 4, 5 is private keys, and g to the power lambda 1, 2, 3, 4, 5 are public keys. So, well, what happens here is that there is a binary tree, and each node in the tree has a public-private key associated with it. So the leaves in the tree are user keys. So we have lambda and g to the power lambda. G to the power lambda, the public key is public, and lambda, the private key, is obviously not known to anyone. So let's say, let's say user 5, by knowing public key of user 6, lambda g to the power lambda 6, can derive g to the power lambda 5 times lambda 6, which is like the Diffie-Hellman secret between users 5 and 6. So what if this Diffie-Hellman secret is used, or like hash of it maybe, is used as a private key for this node, and then the public key for this node is g to the power that, and this is public. Then to derive the kind of private key on the top, you would need to know, like user 5 would need to know public key of user 6, public key of user 7, and public key of this node in the tree. So, which means that the user 5 would need to do like logarithmic number of operations to derive a shared secret, which can be derived by anyone who is in this tree. So anyone in this tree, users from 1 to 6, can derive this GR key, which is the session key. So let's say in a new session, a new user joins, and he publishes the public key, and then this user can derive the group session key for like when this user is in place, and other users, if they believe this user should really be in this tree, also can derive the same key, and then this key can be used for the session. So, and this like granting permission in this session requires logarithmic number of operations from every user, and revoking access means that they have to recompute the tree. So each user does again like the logarithmic number of operations. So this is kind of a great, very elegant approach, and it can be used for like group chats and stuff. So what's wrong with that approach, or is there anything wrong? Well, first of all, it has this perfect forward secrecy property. So if you want to share the past data, you kind of need to. The user who wants to know the past data wants to be able to have access to all the past messages. So which is either encrypting those messages explicitly for that user, so kind of bypassing this whole thing, or encrypting all the session keys from the past. And I don't know how safe is that. That's the first thing. And second thing is that what if you want to kind of go with a different granularity than those sessions? Like what if you want to share data which is from half of one of the past sessions to like half of some other session, right? In this case, you would have to send really encrypted messages to this user. And also what happens if we want some stranger to write to this stream of data. So let's say right now we had everyone having access to this collection of data, right? So all M UP users can read and write. So what happens if we want to have some different user who can only write but cannot read, right? If we want to do that, well, here this session key is kind of known by everyone, so it's kind of like a symmetric key. We don't want the writing character to know this. Well, in principle, if we kind of modify this original definition and use this private key not as like symmetric key, but as private key for public key encryption, maybe it would be possible to calculate public key for the strangers, so strangers could write, but then the strangers would need to update this key every time you change the session. So maybe that's all right, but it kind of excludes the headless strangers who only like know the initial public key for the thing, and that's it. So this stranger, like in the best case scenario, would need to be like to have the read access and update the public key every time it's updated. So it's it would probably exclude some IoT use cases. Anyway, so, and if you use proxy re-encryption for this kind of thing, well, first of all, we call the stranger Enrico. So this Enrico encrypts with, so the data is always encrypted for Alice's public key, and you don't change the key under which data is encrypted, and Enrico, the writing character, needs just to only know the public key, and then you just tell the group of proxies which like who you like granted access to in a cryptographically secure way. So you give the re-encryption keys to the group of proxy, and then of course Enrico cannot read the data. He just encrypts for Alice, and then let's say Bob and Charlie read the data after the proxy transformed data to them when it could. So a grant and revoke here would be just O of 1, because Alice would just grant permission to like let's say Bob and Charlie and whatever, and Bob doesn't do anything with that. Ursula technically would just need to accept the re-encryption keys, but also she needs to validate that they are valid re-encryption keys. So it's, let's say, O of 1. And to decrypt messages, well, Bob would need to do like O of 1 operation. Well, technically M operations, where M is number of proxies you distributed the re-encryption key with. And encryption is just encrypting for one public key. So Enrico wouldn't even have to be connected to internet. Enrico just can have the hard-coded public key, and then produce everything encrypted for this public key. And then Alice can just figure out who to share the data with. On the downside, this Alice is kind of the admin of the group. So the Alice is a kind of real character. It probably can be made into a group of characters, though. But yeah. Okay. So, and now, like, is it possible to make this sharing granular? So imagine that you have, I don't know, multiple types of data, or maybe data distributed over time. So how to share different pieces of data separately? Well, one way would be this. So we call it kind of encryption for labels, but basically you can have Alice deriving different private keys for different labels, and there are different public keys corresponding to them. And then if you want to have data to have like multiple labels, you just encrypt data with symmetric key and encrypt messages with symmetric key, and you encrypt a symmetric key with derived key for different labels and attach all of that together, right? And then if you were granted access to some label, proxies have re-encryption key from this label's private key to their public key, and they will be able to decrypt the message. So this, in principle, can be used to share, let's say, ranges of time ranges of data. So, for example, imagine you have different labels for every year, every, I don't know, month, every day, or like whatever granularity you want to have. And then you kind of all the data is encrypted with symmetric key, and each symmetric key is encrypted for like, today's public key, and also for this, let's say, week's public key, this month's public key, and then you have there's several encrypted symmetric keys and the ciphertext combined together. So, and then you can, let's say when you give access, you say, I want to give access from, let's say, this day to this day, which would mean I want to give access to like all the like full years in between, or like full months in between, and some full days in between. So you create this number of re-encryption keys, which is in the best case like the number proportional to log of time range, and well, if you don't use days, but kind of do binary. So you would have number of re-encryption keys proportional to log of this time range, and grant access this way. Well, the problem with this approach is that this would require Alice to create this public-private key pairs for all the, like let's say every day, right, in advance. But there are, if this is really needed to share like time ranges of data, it's there exists attribute-based proxy re-encryption, where like Enrico can say, I encrypt data for this label, and then Alice can grant access for like a bunch of labels. Right. So, well, anyway, this is kind of coming to the end of the talk. So, and yeah, I reviewed the sharing data using the trees of keys versus sharing data using proxy re-encryption. And I believe that if you want perfect forward secrecy, then probably multi-user like data sharing using trees of keys is probably better, but if you do need to share to share history, then proxy re-encryption is clearly better. When you have write-only participants, I think it's still better with proxy re-encryption. And yeah, if you want to impose any limits on the any kind of limits to how much data you can decrypt, for example, or like any limits on like when you want to, if you want to share data only when some transaction happened or whatever, then it's probably better to do proxy re-encryption as well. And also, if you need revocation, if you believe in revocation, proxy re-encryption is better. Of course, you may say that revocation probably doesn't work, because if you had access to this data, you probably could have just downloaded all this data and now you have access to all of it. Well, I mean, that's kind of true, but maybe you didn't, or maybe you had some limits on how many re-encryptions you can do, and then actually revocation makes sense. So yeah, that's kind of as a yeah, and I wanted to point out that our new Cypher team is actually here at the summit. So after the talks, if you will have more questions, we can talk to them.
So the question that I have is that is it true that it also provides a measure against actually linking of content that I was able to decrypt to some other to some ciphertext that other people know that it's needed. So basically, if I'm granted access through proxy re-encryption to, let's say, somebody's medical records,
right,
then even if I can read it, I don't want to be. So one advantage over current swarm encryption would be that I cannot disclose any information that would, in addition to providing the data, also prove that it's that particular data.
So do you want to not be able to, let's say, for example, you want to not be able to have access to, like, who else has access to this data?
No, that we also have. What I want is, so the problem with swarm encryption, as was pointed out by one of your colleagues, is that if I have access to some medical records where the root hash of the ciphertext is in the blockchain, and I have been granted access to an ACK and access control, right? Then I can disclose some information which proves which not only discloses the data, but also proves that it is linked through the Merkle proof to that particular record in the blockchain. And I was told that this proxy re-encryption is actually protecting against this. And I don't quite understand why and how.
Well, I mean, it can protect, I guess. Like, for example, if you... Depends on what you're hashing, of course, right? So if you... Let's say you hash the ciphertext, which is produced by public key encryption. So maybe it has a symmetric key encryption part, doesn't matter, but if you hash the whole thing, the kind of EC part and the ciphertext part, or maybe just the EC part, right? In this case, if you do that, then I guess the reader of the data, he will get a completely different ciphertext. But actually, in our case, in our setting, the reader of the data gets the ciphertext which is undecryptable by him, right? And then he asks the proxy to transform. So if you... Yeah, it's a good question. Which data you would link, right? Because if he has access to, if you link their originally like encrypted data, right? Then I guess if the reader has access to that anyway, he would be able to link, right? Well, the good thing is that the data which the reader actually can decrypt is the ciphertext is different from the original ciphertext. So. Well, you probably would be able to have it linked in the re-encrypted form for some different readers. But yeah, if you said that one of our colleagues pointed this out, yeah, I guess they're all here, so we can talk more. Yeah.
Can you undo the proxy re-encryption?
You mean to put the proxy re-encryption different way, like from Bob to Alice?
Yeah, exactly.
Right. Yeah, so there are algorithms, proxy re-encryption algorithms, which are unidirectional and bidirectional. So ours is unidirectional. So if you encrypt from Alice to Bob, it's from Alice to Bob, not the other way around. But there definitely are algorithms which are both ways. So you have either, we use unidirectional.
And is there any difference between them apart from this?
Well, I mean, there are there are different properties of different proxy re-encryption algorithms. For example, ours is CCA secure because we're based in it on ECIS. There are some CPA secure proxy re-encryption algorithms, there are also like I think kind of anonymous proxy re-encryption algorithms where you, in principle, could not de-anonymize. Let me think. So there are different like anonymity properties for proxy re-encryption algorithms, so there's a bunch of stuff.
Okay, so thank you very much.